Okay, so we start from the Ch4 transformation here. Okay, so Ch4 transformation gives us you can transfer from the very simple geometry to more complicated geometry. Okay, for example, we have already done is if I transfer this circle with a radius c, okay, 半径是 c. Okay, we know this is c, part of this c, and that negative c is our critical point, two critical points. So for this circle, we're passing through the two critical points. Okay, so through this Ch4 transformation, we transform to the flat plate. Okay, that's we already demonstrate. Okay, and the second thing here is if we have a circle, okay, with a radius a here, and this a is greater than c. Okay, a from here to here is a, and c is from here to here. Okay, so the a is greater than c, so this is a bigger circle. Okay, 这是比较大的圆。Okay, and through the transformation, you see, it will become elliptics. Okay, 它变成一个椭圆形。Okay, so that will be and so we can write down all kind of the flow around the elliptics. Okay, this is a flow around a so-called uniform flow, and this is the flow. We apply the circular theorem, and this is the flow over a cylinder with angle tag alpha. Okay, that will be something related to this. Okay, the flow pattern for this complex potential will be flow over a cylinder with angle tag alpha here. Okay, so this is the complex potential we have for this flow field. And through the Ch4 transformation, we can convert to the flow over elliptics, okay, with angle tag alpha. So this is once we through the Ch4 transformation, this mapping function here, and we can convert to this. Okay, so this flow field or this complex potential will represent the flow over the elliptics with angle alpha. Okay, so that's how we did before. Okay, and we're also talking about the flat plate L4 here, right? So we know the flow if our circle is passing through these two critical points through the Ch4 transformation. In the z plane, okay, become so-called a flat plate. So flow around a cylinder with angle tag alpha become the flow over a flat plate with angle tag alpha. Okay, so we can have this kind of the transformation and to understand how the flow over a flat plate look like. And since previous time we're talking about, okay, when flow over a flat plate, we find a stagnation point here and here. This is two stagnation point. Okay, and then at this trading edge here, okay, at the trading edge here, and we find out the trading edge here, our velocity in z plane will go to infinity because the dA dot dz will be so-called the dz dA dot is approach to 0, and dA dot dz will be approach to infinity. So that is impossible in the flow field because at this point here, this impossible flow is so-called become infinity. So how do we fix this problem? Okay, so this is not relative flow. Okay, this flow is not real. Okay, we do the transformation. However, we find out flow over a flat plate. Okay, for this point here, we got a velocity approach to infinity. That's impossible, and this is not real. Okay, 在物理上面或者是实际上面，我们不可能出现。So 我们要怎么样看待这个问题，或怎么样修正这个问题 ？So how do we fix this problem? Okay, how to fix problem is using so-called Coulomb condition, and I will introduce what's a Coulomb condition. Okay, so the idea is like that. Okay, since the stagnation point, the original is here, right? It's this point and this point, and if I can move this stagnation point and then change to this point here, and I can solve my problem. Right? Because the stagnation point gives us what? Velocity equal to 0. Okay? And I force this at this point the velocity equal to 0 instead of infinity. Okay? So in order to satisfy this, we're using the Coulomb condition. And in real flow, as you can see, this is flow over L4 here. If the separation point here is this, okay, original separation point is here, right, at this location. However, for in the reality flow, okay, we all find the separation point is very near the trailing edge. Okay, they cannot happen separation point here. Okay, separation point most will be appearing near the trailing edge here. Okay, this is separation here. So we have very close to the trailing edge. So that's similar to what we did, okay, by applying the Kodak condition. Okay, so Kodak condition is for body with a sharp trailing edge, like here, okay, with a small angle attack. This is with angle attack. Flow is uniform, but we have L4 here with an angle attack. Okay, and the flow will be adjust itself. Okay, in such a way what the real separation point, okay, this separation point here will be coincide with the trailing edge. Okay, 它会自动去调整，把这个 separation point 移到这个位置来，跟 trailing edge 一样。Okay， 这是它自然界它自己会去调。Okay， and then so here we can apply, okay, how can we shift the separation point? For example, for this case here, separation flow over a cylinder. We have the separation point here, separation point here, right? And then how can we change the separation point to here, to here? Remember, we can apply what? Circulation, right? You have done that before. So we can use in so-called vortex or circulation to relocate our separation point. Okay, we can change our separation point by apply a circulation or vortex around this cylinder, and our separation point will be shift or change from this point to this point. Okay, and if I did that, as you can see, through the Ch4 transformation, our separation point will move to the trailing edge here instead of here. Okay, so this is a kind of very, very interesting, okay, condition. We have to kind of in addition to fulfill, okay, in reality we have to apply the Kodak condition, and this Kodak condition allow us to apply a circulation on this flow field, and this circulation once I apply circulation on this flow field, our separation point will move at this point to this point, and that will fulfill our condition. Okay, so that's called the Kodak condition. We have to apply. Okay, so according to the Kodak condition, we have to move the trailing edge. Okay, by using so-called clockwise. Okay, the circulation. Okay, and later I will do that. Okay, and remember why, okay, we can apply the circulation on the L4 here without any, because the flow is always what? Is irrotational, right? Yeah. For the chapter 4, we are talking about all this potential flow. A potential flow is incompressible, implicit, irrotational. Irrotational means there is no vorticity at all. Okay, and as you can see, how can we apply the circulation? Circulation is already had this some kind of vorticity inside. Okay, and how the flow will be we use irrotational, but without the circulation, without the vorticity. And so this is L4 here. So we kind of conditionally apply the circulation around this L4 here. And once we apply the circulation around this L4 here, we kind of what? Our irrotational flow. Okay. However, since our uniform flow is rotational, far downstream also irrotational, because this is uniform flow. Only very near the L4 here, we apply the circulation. And this circulation here, the strength of this circulation is very close to what? If you study the so-called starting vortex, when you have a flow suddenly start, you will, at the trailing edge here, will generate this kind of this vortex. We call this vortex the starting vortex. And this starting vortex is what? Is a counterclockwise rotation, right? This is rotate like this way, and this is rotate like this way. So these two will be cancelled. So yes, you can see when this move far away, this circulation vorticity strength will be equal to this vorticity strength, and this 2 will be cancelled because the vorticity is equal to 0 within this circulation long here. Okay, so that's why we can apply the circulation, and this circulation will account for this starting vortex strength. Okay, so that's we already mentioned that in chapter 3, I believe. Okay, this is from the chapter 3. We have this view graph, and this view graph account for when flow over air foyer. Okay, and we can apply the circulation, and this circulation have the strength of the applied, how much the strength for this circulation have to be applied should be satisfied so-called Coulthard condition. Okay, Coulthard condition just X what is try to what? Try to move the stagnation point and by apply the circulation and allow this stagnation point move from this point to this point here. Okay, and our trailing edge here will be the stagnation point. Okay, so that will be the Coulthard condition keep us. Okay, and we also have the what? We also have here, okay, I think if you remember this, we also calculate the lift around the air foyer. Lift around the air foyer equal to low view gamma. Okay, B is this width, right? This is so if the 2D closed section air foyer with unit span, okay, L over V, B is in this span, right? So there's a 2D air foyer is L over B. L over B is equal to what? Low V gamma. This is our lift for 2D air foyer. So this kind of we can apply this called the Coulthard-Jacobi law. Okay, the lift or y direction force will be equal to low V gamma. Okay, that's a lift that we can generate. If you apply the circulation, you will generate lift. Okay, that's it. So, and how much gamma should be? As you can see here, how much gamma should be? As you can, so we would like to move, right? Originally, our circulation is what? Our circulation, our stagnation point is at this point, right? Because the flow over cylinder with angle take alpha here. Okay, our stagnation point is here because this is symmetric. Okay, and how much we have to move? The angle here is alpha, right? From this point to here, this point is the alpha angle. And then, if you remember, when we apply the circulation, okay, and we can change our angle, we can change our stagnation point, theta s is according to this formula. Okay, in order to understand this, I think I can show you previously, okay, in the 4.2, I believe, or 4.1. Let me check 4.1 first. Okay. 4.1. Okay. Okay, here, right? 4.1 here. So, original we have this flow, right? We have this flow. Okay, flow over cylinder without circulation. Okay, this is the flow over cylinder without circulation. Okay, this is, and then once you apply the circulation with circulation here, we apply the gamma here. Okay, and the gamma will change our stagnation point. Okay, to this point, and this you can find out your stagnation point. Okay, if the gamma within this range, we should follow this, right? Theta s. Okay, the stagnation point is theta s, sin theta s will be equal to minus gamma 4 pi UA. Okay, that will be the equation we're using. Okay, so this is the original point. We shift how many angles, theta s angle, by applying this gamma. Okay, and the angle with the gamma relation, we should be follow this relationship. So we apply the similar formula here. 所以这边我们同样的，我们利用这个公式，我们要改变多少角度，对不对？然后我们要多少的伽马的强度 ？Okay, here. So if you go back to our lecture note here, okay, this is the equation we just mentioned. Okay, 这是我们刚刚用的这个 equation. If you want to change theta s angle how much strength of gamma we should apply. The gamma will be equal to 4 pi UA times sine theta s. Okay, and right now for this case, our theta s is what? Theta s is alpha, because we would like to change our staging point from this point to this point, and the angle here is alpha. So the theta s become alpha here. So this is the exact circulation strength we have to apply in order to satisfy the Coulthard condition. Okay, can you understand the point? So here, this is the circulation. Okay, the strength of circulation we have to apply. Okay, to change our staging point from this point to this point and allow us to satisfy our Coulthard condition. That means our staging point will be exact at the trailing edge. Okay. Okay, so if you understand here, okay, from this equation and change to here, this is the circulation we have to apply, okay, and with this strength, okay, and in order to satisfy the Coulthard condition. 有没有问题在这里？这是非常重要的。Okay, this is very important. Okay, if any question until here, please raise your hand. Okay, 有没有任何问题？这听不懂的。我们为什么 gamma 等于这个 ？Why the gamma is equal to this? Okay, you have to understand. Okay, because we have to satisfy Coulthard condition. What's the Coulthard condition? Coulthard condition is we would like to move our staging point from this point to this point, and the angle here is alpha. And alpha, in order to change our staging point with angle alpha, this is the gamma we have to apply, right? And the gamma strength will be equal to 4 pi UA sine alpha will be here. Okay? Okay, once you understand this point, the rest is easy. Okay? Flow over the cylinder with angle attack, with circulation, you can write down your complex potential. This is uniform flow plus a double flow give you flow over cylinder with alpha, angle attack alpha, and plus a circulation. Okay, this is circulation we apply in order to satisfy our Coulthard condition. So in the data plane, this is the complete potential for this flow field. Okay, and through the Ch4 transformation, okay, this is Ch4 transformation. This is Ch4 transformation. Okay, we can shift to the flow over L4 here, and this L4 here is what? Is a flat plate with angle attack alpha, and satisfy our Coulthard condition. And in order to satisfy our Coulthard condition, this gamma should be equal to this. If you apply here, you will become like here. Okay, gamma divided by 2 pi, 4 pi divided by 2 pi equal to 2 UA sine alpha, 2 UA sine alpha here. Okay, so that will be, we already simplify here. And through the Ch4 transformation, okay, it will change to flow over a flat plate with angle attack, and apply the circulation to satisfy our Coulthard condition. Okay, so this is flow field for this complete potential. Okay, 好 the lift equal to, okay, low U gamma. We already know how much gamma you should apply, right, in order to satisfy the Coulthard condition. And this is gamma is equal to what? Gamma is equal to this. This is gamma we should apply in order to satisfy our Coulthard condition. So our lift is equal to low U gamma, and if you plug in the gamma we have, it will be equal to 4 pi low U squared A sine alpha A. Okay, that will be the, will give you the lift. Okay. Okay, so this is the gamma. Okay, since our gamma, we can calculate the gamma by the so-called circulation, right? The integral, line integral around a closed loop. 我们可以去积分一个 loop， 对不对 ？loop 怎样去得到我们的 gamma？ In the z plane, we have this, right? In the zeta plane, okay? In the zeta plane, we have this. How about in the z plane? Okay, in the zeta plane we have this, because the flow over cylinder with circulation we have this. And how about the flow over a flat plate, okay, with angle attack with circulation in z plane? we also can do what? Do the circulation, right? And we already tell you the circulation through the transformation, this circulation strength will not change. Okay， 就是 circulation 这个强度在经过 transformation， 它的强度不会改变，不需要改变。And we also can prove by this. As you can see, we can choose a closed loop C sub 0 here. It's a very large circle. As you can see, for the Ch4 transformation, okay, you see the Ch4 transformation here. Okay, where is Ch4 transformation? Let me show you. Okay, this is Ch4 transformation, right? This is Ch4 transformation. Okay, Z is equal to when Z go to infinity, whatever, this approach to 0, right? So Z will be equal to 0. Okay? Right? So in the very far field, our Z plane, Z plane didn't change. So it's the same. Okay? So if I search, if I have a Z plane, Z plane is Z plane. I do the large circle circulation, take the circulation here. In the Z plane here. Okay, I also do this large circle. This is very large. Okay, we can go to approach infinity. Very large circle. This is when the Z approach infinity. Okay, Z approach infinity. Z is almost exactly the same as Z. So this circulation, the flow, is the same. Okay, so we don't have to change the circulation. Okay, that's another proof we can do it. So by using that, okay. It also tell you, okay, the circulation through a transformation, we don't have to change. So this lift will be stay the same, okay, through the transformation. Okay, and another thing we interesting in the aerodynamics is so-called lift coefficient, 升力系数, okay. Lift coefficient is defined as is denoted as a CL. Okay, is defined as L divided by 1/2 of the rho u square times length. Length is our co-length here. Okay, so as you can see, our lift here is equal to 4 pi rho u square A sine alpha, and 1/2 rho u square, right? And our L is what? L is our co-length. Co-length here is this is 2A, and this is 2C, and minus 2C equal to 4C, but C is equal to A for this case, okay? If I remember correctly, yeah, C is equal to A because flat plate, right? Because A and C for the, if you remember, A is what? Is a cylinder, right? This is A, the circle over a cylinder. And for flat plate, A is equal to C here. A is equal to C here. Okay, so here is A is equal to C. So as you can see, this will be cancelled. A and A will be cancelled. If you rearrange, it becomes 2 pi sine alpha. Okay, 2 pi sine alpha. So if you plot, okay, usually we plot the angle attack versus CL. Okay, CL versus angle attack. Okay, this is our lift coefficient. 我们的升力系数跟我们的攻角。Okay, angle attack alpha. And as you can see, the slope here. Okay. Because the CL is equal to 2 pi sine alpha, okay? And as for the sine alpha, when alpha is very small, sine alpha almost equal to alpha. So very close to the 2 pi alpha when for small angle attack. So CL equal to 2 pi alpha, and that means the slope here, okay, 它斜率这里 equal to 2 pi, okay? And this just very close to the reality. 我们去做空气动力学的话，给这个升力系数跟这个所谓攻角的斜率刚好是 2 pi. So the slope for the lift coefficient with angle attack, the slope here is equal to 2 pi, very close to the reality. Okay, so dCl d alpha is equal to 2 pi. Okay, let's lift on the flat plate. Okay. And then next, we will go even further, okay? As you can see, okay, if I change our circle, okay, this circle is a radius A, okay, and so this is radius A. However, the circle center is not at the origin anymore. I move to the left M here. Okay, 我把这个 circle 往左移，移多少呢 ？The M. Okay, so the radius for circle is A, and I kind of intention is our smooth curve will passing through this critical point. Okay, but on this here, okay, since the circle is bigger than C here, so this point didn't, this smooth curve didn't passing through this critical point. Only one, okay, smooth curve at the trailing edge here will be passing through our critical point. And as you remember, when our smooth curve passing through the so-called critical point, what happened? We will generate a cusp. Okay, 你如果还记得的话，我们以前 we're talking about the very interesting phenomena for the so-called Ch4 transformation. Okay, and when you have the smooth curve passing through the critical point here, you will generate the so-called cusp or knife edge. Okay, so that's very similar thing we did is what we using this. Okay, we allow this passing through our critical point, so we will generate trailing edge here. However, the leading edge here we didn't passing through the critical point, so this will become this blunt body here. So later you will see this will become the so-called airfoil. Okay, and this spatial airfoil we call the Ch4 airfoil. So if we arrange our circle like this way, the transformation through Ch4 transformation will become the so-called Ch4 airfoil. 所以你把你的 circle 往左移 ，OK， 这个 shift M here, you will generate so-called this, okay, Ch4 airfoil. So in the zeta plane, okay, the circle passing through one of critical points, zeta equal to C, to produce a sharp edge here. Okay, through Ch4 transformation become cusp here, but we will enclose this another critical point minus C. Minus C is inside this circle here. Okay, so we will produce so-called leading edge, and this leading edge with a finite curvature here. Okay, so this will be later. I can show you. This is one very similar to an airfoil shape. Okay, so our circle center is what? Circle center is here. 我们的圆心在这里 ，okay, is equal to zeta equal to minus m, because this is m here. Minus m is the coordinate for our circle, center of a circle. And the radius a, this is radius a here, right? Radius a here. The radius a can be written by two way. From here to here is our radius 2, right? So here to here is a. A is equal to m plus c, so A is equal to c plus m. Okay, c plus m. So since this n is very small number, so we can written as rewritten this. It becomes c times 1 plus epsilon. This epsilon is equal to m over c. If you plug this into it, it will give you this. So m over c is the ratio between our shift over this c here. So this gives you a very small number called the epsilon. Okay, and this epsilon is much less than 1. Okay, so we later I can show you this epsilon will control the thickness of airfoil. Okay, if you move this m is bigger, the thickness here will be bigger. The m is smaller, the thickness will be smaller. Okay, they can control your airfoil thickness. Okay, but anyway, this is epsilon. Okay, is controlled by m over is defined as n over c. Later I can show you this is related to the thickness of airfoil. But anyway, we will consider only very thin airfoil. That means this m compared to c is much less than 1. Okay, even we control a little bit thickness. However, this m cannot be as big as c. Okay, that's a condition. We call this a thin airfoil approach. Okay. So here we try to give you the so-called geometry for this airfoil.